Thank you for joining us. It is my pleasure to share with you this tutorial about energy storage. This time, we are on a virtual environment, but the joy and the passion for power systems remains. Technology around energy battery storage systems is rapidly changing, but the first principles are the same. The intention of this tutorial is to present a general overview of the application of energy storage technologies in planning, operations, and control of electric power systems under an international perspective. My name is David Elizondo, and I am Vice President for Business Development and International Operations at Quanta Technology. I have 23 years of experience in electric power systems. I have been working on the application of energy storage systems for more than 10 years. Back in 2008, 2009, I worked on the feasibility study of an energy storage project for SCE, a utility in California, under California Energy Commission funds for an 8 megawatts, 32 megawatt hour system, which was installed later in 2013. In 2016 and 2017, I directed a USTDA-sponsored project that identified feasible energy storage projects in Mexico, Colombia, and Brazil. It is my pleasure to share this tutorial with you during the next 2 hours. This is the agenda for the tutorial. Part A, background and history of energy storage technologies. Part B, potential of energy storage applications for generation, transmission, and control centers. Part C, a sample of energy storage projects installed around the world. Part D, energy storage market for Latin America. Part E, energy storage regulations. Part F, most beneficial applications for the electric power system. Part G, valuation, business models, and the economics of energy storage. And finally, Part H, conclusions and vision of the future. Part A presents the background and history of energy storage technologies. We will start with a high-level overview of the basic types of energy storage. Our focus is on practical and emerging technologies. We will present an overview of global energy storage projects installed around the globe. We will then continue with battery energy storage projects with a characterization of the technical characteristics and overview. We will keep the proper perspective of this presentation, and we will share energy storage densities compared with other energy storage sources, such as diesel generation. The lithium-ion battery is the technology of choice. Therefore, we will present this technology first. We will also present other technologies such as the sodium sulfur, the advanced lead acid, and the flow batteries. We will close with a summary of key battery energy storage performance criteria. As you can see in this slide, electrical energy storage systems can be classified in 4 main types: electrical, mechanical, thermal, and chemical. This presentation focuses on chemical energy storage. The time scale of the different types of energy storage starts with short duration, which is presented in the green color, and can be a discharge of up to 15 minutes. Technologies of this type include flywheels and superconductive magnetic coils. Medium duration, such as pumped hydro and compressed air energy storage and batteries, can provide a daily storage system and typically can charge or discharge for 1 to 10 hours. Long duration discharge, which includes the technologies in the red fonts, include technologies such as hydrogen storage and can store energy for up to 50 to 500 hours. This presentation focuses on chemical energy storage. Chemical energy storage can be classified in 2 main groups: internal storage and external storage. Examples of internal storage include lithium-ion, sodium sulfur, lead acid, and nickel-cadmium batteries. Examples of external storage include redox flow and zinc bromide. The presentation focuses on proven technologies that are already in service in the electric power systems around the world. These include the lithium-ion batteries, which is a technology with the fastest market growth, batteries of sodium sulfur, and vanadium redox. This slide presents an overview of global energy storage projects. Electrochemical storage, shown with light blue or aqua colored bars in the graph, is the fastest growing technology. Thermal energy storage constitutes about half of the installed base. As we know, the use of hot water tanks is a well-known technology for thermal energy storage. The trends for electrochemical storage continue in the same direction in 2020, particularly for battery energy storage, with more projects installed and battery prices continue to decline. This is a busy slide with many technical details. The audience is invited to use it as a reference. We will talk about four key technical attributes identified with red colored numbers on the table. Items 1, 4, 11, and 12. Item 1, round trip efficiency. Efficiency are typical values which depend on a number of operational variables such as rate of discharge, rate of charge, and duty cycle. However, we can identify two leading technologies in this table with the highest efficiency, lithium-ion and supercapacitors. Item 4, life cycle. Useful life cycle for battery energy storage systems is in the order of 15 to 20 years, considering replacement of key battery components. Useful life depends on the duty cycle, which defines how many times per day or during the useful life the battery charges and discharges. In simple terms, for a simple system that is used once a day, 365 days in a year, we have 3,650 cycles, so it can last about 10 years. Item 11, typical power. You can see values of up to 50 megawatts or 100 megawatts, and right now those are good market trends for installations. Item 12, typical energy values, and you can see values of up to 300 megawatt hours or 400 megawatt hours for lithium-ion batteries. To put things in perspective, this slide shows that diesel has the highest energy density from an energy per volume perspective. Capacitors have relatively very low energy density. However, when we look at the perspective of the lithium-ion battery, we can see that the lithium-ion battery's energy density is 5 times higher than the lead-acid batteries, 50 times higher than flywheels, and 10 times lower than diesel fuel or diesel generation. Lithium-ion battery technology is definitely the market leader. Most modern installations for power system applications are based on this technology. This slide shows the key companies that are active in the market. Typical installations are deployed in the form of containers, as you can see in the slide, as opposed to typical brick and mortar stationary construction. Typical life of battery energy storage using lithium-ion technology is life cycle is about 4,300 cycles, and energy efficiency is in the order of 90%. Sodium sulfur is probably the second most common battery technology. A challenge with these installations is the operating temperature, which is in the order of 270 to 350 degrees Celsius, and the need to use electric heaters to keep the temperature in that levels of magnitudes. There are quite a fewer companies active in the market when compared to lithium-ion batteries. Typical life cycle is 4,000 cycles, and energy efficiency is in the order of 70%. The picture shows a real-world installation of this type of batteries in the US, along with a wind plant that you can see in the picture. Advanced lead-acid batteries have typical applications for backup power or at substations for DC power. This slide shows the key companies that are active in the market. Life cycle is in the order of 2,200 cycles, and efficiency is in the order of 80% range. Examples of energy storage include redox flow and zinc bromide. Flow batteries efficiency is in the order of 60%, quite low compared with lithium ion. The system uses pumps to maintain circulation of the fluids within the tanks. Life cycle is similar to the lithium-ion batteries. Installation of this type are still at the pilot projects or research and development types. When planning or specifying a battery energy storage system, this slide considers the minimum parameters to review or specify. First one, life cycle. Second, round-trip efficiency. C rate, which determines how fast can the battery charge or discharge, and is a ratio between power and energy. The depth of the discharge, expressed in a percentage. The capacity degradation, which depends on the duty cycle and the depth of charge. Sometimes there is a need to replace battery cells. Response time, typically expressed in milliseconds. The footprint, square feet or square meters. Safety, which is of paramount importance these days. And finally, the install costs, the operation and maintenance costs, the warranty cost, the commissioning cost, transportability, and the degree in which the battery can be connected to an energy management system. We are now in Part B. Part B covers the potential of energy storage application in transmission, generation, and control centers. The 5 topics to include in this Part B are energy storage, location, location, and location is the single most important item when citing an energy storage project. The potential applications for energy storage, the 17 applications for energy storage that have been reviewed and organized by Sandia National Lab, the importance of a stack application under a theoretical approach, and to complement the importance of a stack application as a sample of actual projects that are installed in the field. So we are comparing theory and practice. As discussed before, the locational aspect is of paramount importance for energy storage applications. This diagram shows how versatile the locational aspects is of paramount importance for energy storage applications. This diagram shows how the technology can be used along the generation, transmission, or distribution segments of the electric power system. Battery energy storage systems have been found ideal to complement the variability of wind and/or solar generation, to resolve transmission constraints under a single contingencies, and to defer investment in distribution systems. In red fonts, you can see in the slide how real-world applications can actually be deployed, while in the Magneta color, we present future possible applications of energy storage in the electric power system. Applications for battery energy storage systems. There is a significant amount of research about battery energy storage systems, and different sources document slightly differently the applications, particularly when we compare the American continent with Europe and Asia. After our literature review work, we recommend to adopt the 17 applications that have been documented in a report developed by Sandia National Laboratories in the US. The application definitions depend on a number of items such as the energy matrix. Are we talking about hydro-based systems, thermal systems, or other composition in the energy mix? How is the market structure and design? What are the type of products in the market? How they are valued, and therefore, how are they compensated? A matrix of 17 applications for battery energy storage will be presented next. There are 5 categories with at least 2 applications of battery energy storage systems for each of the categories. Category 1, using electric energy storage as an electrical energy supply. As such, we can apply battery energy storage as a capacity source or as an intermittent source to shift energy in time. Category 2, using energy storage as an ancillary service to provide services such as load following, area regulation, electric supply, reserve capacity, and voltage support. Category 3, using energy storage as a part of the grid. We can use in this category 3 as a transmission support, transmission congestion relief, transmission and distribution of grade deferral, and substation on-site power. Category 4, using battery energy storage to support the end user or the utility customer. Time of use, energy cost management, demand charge management, electric service reliability, and electric service power quality. Finally, category 5, using energy storage to support the integration of renewable sources, renewable energy time shift, renewable capacity firming, and wind generation grid integration are the applications that are possible under the National Report of Sandia National Lab. It is well understood by the electric power industry that battery energy storage systems can provide multiple different services to the power grid. These services cover a very wide range of capabilities and represent different possible revenue streams. It's very important to identify different applications for a single battery energy storage system. For example, this slide shows how transmission and distribution of grade deferral and voltage support are 2 applications for a given battery energy storage system that can be used. This slide presents a theoretical representation of all the potential possibilities that can be used for battery energy storage system and has some legends to map how the pairing of different applications are actually possible from a practical perspective and categorized as excellent, good, fair, poor, or incompatible. As you can see, the transmission and distribution of grade deferral and voltage support are excellent applications that can be used for a given system. This slide presents a summary of projects that are installed in the field. As you can see in the last column, most of the projects have more than one application, such as item number 3, the Node 3 storage project, which is used for area or frequency regulation, is also used for voltage support, and also used to firm the capacity of this renewable source. One of the first research and development projects installed in the US is item number 8, the Tehachapi Wind Energy, which shows up to 10 battery energy storage system applications. This is a research and development project, and therefore, not all the applications can be used simultaneously. However, it proves the concept of the different applications of battery energy storage system. The last row in the column of the table show the applications that are most used, which are area frequency regulation with 12 out of the 17 projects that are shown in this table, and renewable capacity firming with 6 out of the 17 projects that are shown in this table. We are in part C which presents actual energy storage projects installed around the world from a practical perspective. This part covers the following items: an overview of energy storage systems, the components of energy storage systems, an indicative layout of a mobile container-based solution for battery energy storage systems, an overview of key energy storage deployment in the US, recent utility scale energy storage projects in the US and Latin America, and finally, a deep dive into energy storage projects for California-based utilities, particularly San Diego Gas and Electric and Southern California Edison. The most basic components of a battery energy storage systems include the batteries themselves, a power conversion system with an AC to DC inverter, an AC transformer, AC and DC switches, and monitoring and controls. Most, if not all, modern installations are deployed in the form of containers for battery energy storage systems. The most basic components of a container include the common rack system, which is a standard rack for the battery cells, the system controller, the purpose-built modular building and HVAC to control and monitor the temperature in the container, the battery cells, the battery management system, and the common battery module. An indicative layout of a transportable 1 to 2 megawatt hours battery energy storage system is presented on this slide. Transportable storage systems are starting to appear. They are typically mounted over a platform of a trailer, as you can see in this picture, and they are becoming more and more common in our industry. This slide presents energy storage deployment across the US. There are several megawatt scale projects that have more than 8 years in operation. The key geographical areas in which these systems are deployed include the PJM, which is a market area in the Pennsylvania region in the US, the California market in the west part of the US, the ERCOT in the Texas state, and those applications are driven mainly by frequency regulation application, by energy storage mandates, and by the efforts to integrate renewable energy, particularly wind. This slide presents recent utility-scale projects that are deployed in the US. The largest battery energy storage system is contracted as 100 megawatts, 400 megawatt hours, and there are several 20 to 40 megawatts units that are operational in the US. We will present details of items 1 and items 2 identified in the table in the following slides. This project is one of the first battery energy storage projects of relatively large scale for Southern California Edison and the Department of Energy on an industry initiative. The owner is Southern California Edison. As we discussed before, it's an 8 megawatts, 32 megawatt hour system, and is located in Tehachapi, California, nearby a wind farm, and the year of installation was 2014. The driver for the installation, this project was funded by Southern California Edison and the Department of Energy under a government funds. And this project evaluates the performance of grid connected battery energy storage systems to assist in the integration of large-scale wind generation. It's a research and development project, and the project had many purposes, including to provide voltage support, grid stabilization, decrease transmission losses, diminishing transmission congestion, increase system reliability, and the fair transmission upgrades. It has, as we discussed before, more than 10 applications under a research and development initiative, and proof the concepts of that these applications are feasible and can be done. This slide presents a success story for Southern California Edison, in which energy storage was purchased under a competitive process. The owner of the project is AES, an American company. The size of the energy storage project is 100 megawatts, 400 megawatt hours. The location is California in the US, and in the year installed is 2021. AES Corporation was awarded a 20-year power purchase agreement from Southern California Edison to provide 100 megawatts of battery energy storage. The awarded PPA is really representative of a new age in which energy storage is used as an alternative to constructing and building a traditional peaking power plant. SCE, the utility that lead the power purchases agreement, reported that over 1,800 offers were submitted for the power purchases agreement, including offers for thermal plant construction, and among those offers, energy storage was selected. For the first time, energy storage has been selected in a competitive solicitation with other peak and flexible power capacity alternatives. So it's a success for energy storage as a competitive process. This is a success story of battery energy storage systems in Latin America, particularly in Chile. It's a 20 megawatt, 40 megawatt resource unit located in Mejillones, Chile, and it was installed in 2012. The driver for the installation was the construction of a 544 megawatt thermal power plant in the town of Mejillones in the northern part of Chile. And the plant provides electricity for this important mining region. Is an application of energy supply reserve, and the technical narrative indicates that by meeting the reserve obligations of the plant with this energy storage facility, the generation owner was able to increase the power being generated to its customers from the thermal power plant by 20 megawatts, and therefore increasing the sales and additional revenue to pay off for the battery energy storage application. This storage unit has been successfully performing its critical function as a reserve capacity as dictated by the system operator since commissioning in December 2011. This slide presents a summary of energy storage projects that are being installed in a U.S. utility, particularly San Diego Gas and Electric. As you can see in the slide, there are at least 7 sites for energy storage projects already installed in this electric power utility service territory. Projects are a variety of high and relatively medium size energy storage projects. On the small to mid-size project includes Pala 1 and Pala 2, which are 500 kilowatts, 1500 kilowatt hours size, and Pala 2 for 1 megawatts, 2 megawatt hours size project. On relatively large size projects include Escondido, 30 megawatts, 120 megawatt hours, and El Cajon, 7 megawatts, 30 megawatt hours projects already installed. This slide presents another California-based leading utility, Southern California Edison, and shows a list of current and past energy storage projects. As you can see in the slide, this utility also shows a total list of 7 projects, and there is variety of battery energy storage system sizes and installation, including applications at the transmission and distribution systems. We will present an overview of the item that is shown in red fonts in the slide, item number 7, which is the Allison Canyon, the 20 megawatts, 80 megawatt hour system. This project is quite particular because it's now part of the bid system under the CAISO market rules for day-ahead and real-time dispatch, and is being used as another generation unit. This is the Allison Canyon Energy Storage System overview. It's provided by the manufacturer that is shown on the slide. It's a first large-scale utility application for this manufacturer, and it's a 20 megawatt, 80 megawatt hour comprised of two identical systems. Each of these identical systems is connected to a unique 12 kV distribution circuit out of a substation of Southern California Edison called Mira Loma. This is the Allison Canyon system architecture. It's comprised of 2 times 10 megawatts by 40 megawatt hour system. The schematic that you can see on the left side of the slide includes the battery pack that is shown with blue color, the inverter that is shown in aqua color, the transformer that is shown in green color, and finally the switchgear in 12 kV that is shown in pink color. A picture of the field components are shown on the right side of this slide, particularly and in the order of transformer, the low voltage switchgear, the inverter, and the battery pack. There are a few constraints that this Allison Canyon energy storage system found along its implementation. The project had a very short timeline, and therefore it was not possible to connect one single system, 20 megawatts, 80 megawatt hour, at the subtransmission voltage, 66 kV. Therefore, the system had to be split into two systems, each of them connected to a distribution circuit of 12 kV. As a result of being interconnected to a distribution circuit which is actually serving customers, the operation of the system is subject to the following constraints: a maximum ramp-up rate of 10 megawatts per minute, and a charge constraint ranging from 3 megawatts to 9 megawatts based on the season. This Allison Canyon energy storage system is operating in the California ISO wholesale energy market and participating in the energy and ancillary services market. The asset was built and commissioned by Southern California Edison Transmission Distribution Organization and is transferred to Southern California Edison Generation Organization for long-term operations. Part D, Energy Storage Market for Latin America. In this part, we will explore and evaluate the characterization of the market for energy storage in Brazil, Mexico, and Colombia, and compare it to the US market. This slide presents energy storage market potential. The market potential was developed using a fundamental approach for each of the three countries. The market potential considers the technical, the economics, and the regulatory state of each of the countries: US, Colombia, Mexico, and Brazil. A bottom-up methodology based on the 5 categories and the 17 battery energy storage applications, as documented in the Sandal report, were developed. These market figures represent a 10-year look ahead for the battery energy storage values. As you can see, there are 5 categories, and the market potential for the US is in the order of 65,000 megawatts to serve the demand. The market potential for Colombia is 480 megawatts. The market potential for Brazil is 5,600 megawatts, and the market potential for Mexico is 2,333 megawatts. There are economic values that represent the economic potential in net present value in millions of dollars that are also shown in the table. This slide presents the bottom-up methodology for each of the 17 battery energy storage applications as documented previously. It also shows typical battery energy storage capacity size in hours that were assumed for each of the 17 applications. It shows the same values that were presented in the previous slide, just includes the detail of each of the 17 applications for each of the countries: Colombia, Mexico, Brazil, and the US. Thank you. Part E, Energy Storage Regulations. In this Part E, we will share with you energy storage key drivers in California, an overview of renewable portfolio standards targets in California, variable resources penetration in countries like Chile, the foundational work for regulations review that was done in the US, key regulations dictated by FERC in the US, a deep dive in the regulations that are most profound impact have taken in energy storage, drivers for energy storage in the US, emerging best practices for the US, and finally, a summary of regulations in Mexico, Brazil, and Colombia. It is important to define and understand what are the key drivers that are moving to push forward energy storage in California, one of the most progressive states. California has environmental objectives, particularly to reduce by 40% greenhouse gases and its emissions by 2030 and have 50% of the generation by the renewable portfolio standards from renewable sources and double the energy efficiency by 2030. There are other mandates by the state regulator, the California Public Utility Commission, to the utilities that are physically located in that state. And there are other efforts that are driving energy storage to move forward in California. As a continuation with the previous slide and considering California as one of the states, one of the questions that has been raised in the utility industry is, what is the role of energy storage and how the targets of renewable portfolio standards should be reached? Are we going to move forward and deploy distributed energy resources along the utility, or are we moving forward to deploy utility-grade energy storage? What is the role of energy storage between a distributed energy resources approach versus utility grade? Unfortunately, there are no clear answers to those questions, and it really depends on the specific utility and the specific regulation around that utility. In continuation with the previous discussion about renewable portfolio standards in the US, this slide presents a summary of variable resources penetration in Latin America, particularly Chile. Per the expansion plans of the Coordinador Eléctrico Nacional, we can see that there is a lot of wind energy and solar energy being planned for deployment, and the energy bids are being highly competitive in Chile's energy auction. And in today's electricity power, it may be better to buy energy rather than self-produce it. So renewables are a key part of the growth for Latin American economies and the power system in that country, particularly Chile. This table presents a list of the most relevant regulations by FERC, the regulator in the US. Certainly, regulations have played a key role in energy storage deployments in the US. We will present a summary of the key language of the regulations identified with red fonts on this slide, particularly FER Regulation 755 Fast Frequency Regulation, which established the principle of pay for performance, Regulation 784 Third-party provision of auxiliary services and accounting for energy storage, which removed barriers to third-party storage providing ancillary services, Regulation 794 Frequency response and frequency bias, setting reliability standard, which impose stricter requirements for frequency response, and at the end 890 open access, which modify the open access rules to include non-generation resources for ancillary services and transmission planning. In this slide, we present a summary of two regulations that really move forward energy storage in the US. FERC Order 890 of 2007, which is titled Preventing Undue Discrimination and Preference in Transmission Service. Pretty much the order modified the open access rules to include non-generation resources for ancillary services and for transmission planning. The second order that we will present in this slide is FERC Order 755, enacted in 2011, which presents the frequency regulation compensation in the organized wholesale power markets. This order established the principle of pay for performance. It created the fast frequency regulation ISO tariff and pay for performance under a specific ISO tariff, which stimulated regulation markets and logically attracted energy storage. This order created new compensation rules for frequency regulation to recognize the value and speed and the accuracy of a better performing device and to better tie compensation directly to how much and to the quality of service provided. The order increased pay for faster ramping resource, which directly benefits storage options such as batteries and flywheels, and created two-part payments, one based on capacity, two based on performance. Continue with a summary of key regulations that affected or impulsed energy storage in the US. FERC Order 784, enacted in 2013, third-party provision for ancillary services, accounting and financial reporting for new electricity storage technologies. This order practically removed the barriers from third-party storage providers to supply ancillary services transmission. Now, operators and not only ISOs must open ancillary services to third parties. The rules on obtaining market-based service rates were modified to remove these barriers to storage. The second order, FERC Order 794, enacted in 2014, titled Frequency Response and Frequency Bias Settings Reliability Standard. This order approved NERC standard BAL 003-1, which created stricter requirements for ISOs and other entities to have sufficient frequency response to disturbances. As we discussed in the last 2 or 3 slides, the US really moved forward with a lot of regulations that really move forward energy storage in the US and allow projects to happen. Uh, the situation in Latin America is different. There are countries that are moving along with potential new regulations, but there is still a lot of things to do. On this slide, we will present to you a summary of one of the key aspects for regulators to move forward energy storage. One of the key items, and is similar to Brazil and Colombia, is to define energy storage as an independent asset class and remove it from the bucket of generation, transmission, or distribution. The second item, also important, is to consider battery energy storage as an additional item for transmission and distribution expansion plans. It's not going to be the solution for every problem. However, in specific circumstances, it can be better than the traditional alternatives. Move also into ancillary services being provided by third parties. Pay-per performance could be another option depending on the need of the system. That's pretty much also the case. Provide cost-based tariff for grid support services depending on the structure of the tariff design and other items. So in summary, there is still a lot to do for the regulators to really define an even land field for energy storage in the systems. Part F, the most beneficial applications for the electric power system. We will continue with a refresh on the inventory of our 17 applications that we have been discussed during this seminar. We will share with you the top use cases for battery energy storage based on number of projects installed, and then we'll be sharing with you sample of benefits of applications for area regulation, number 4, application number 16, renewable capacity firming, application number 2, electric supply capacity, application 7, transmission support, application 8, transmission congestion relief, and we will finalize this part F with a sample of potential projects for battery energy storage in Colombia. I presented it before, and we present once again the 17 applications as a reminder to the virtual audience of the applications that we have been reviewing in this seminar. What are the top use cases for electrochemical storage? As you can see in this plot, the use cases span over a large spectrum of applications. Based on the total number of projects, energy time shift and renewables appears at 2 of the top 4 applications. NERC, the reliability console in the US for bulk power systems for voltages 110 kVA and above, has identified issues due to inverter control generation sources. Battery energy storage can be a potential solution to address fast frequency response. For issues like ramp rate control, frequency response, curtailment, forecasting, energy shifting, transmission congestion, battery energy storage has proven to be effective. Of course, the role of storage in renewable integration depends on the host system needs and the economics. With respect to renewable interconnections, a battery energy storage can improve hosting capacity and investment economics by providing reserves to control the forecast error of wind and solar generation harvest, can provide smoothing frequency and voltage fluctuations, which are inherent with intermittent power resources, improve the energy value through firming and shaping the energy product, increase the capacity factor and value, among others, as this slide indicates. The total amount of storage versus solar or wind depends on the economics of each of the projects. This graph shows how erratic the power output of a solar PV plant can be. PPV in the green line on the plot is the direct output of the PV plant. PVS is the red line on the plot and is the direct output of the battery energy storage system. Pout is the blue line in the plot and is the combined PV plus battery energy storage. Algorithms that run in real time are used to control the power output, which is the total output within pre-identified limits. As the graph shows, the blue line provides a less erratic power output. This is a classical application to evaluate the effectiveness of battery energy storage for N-1 conditions in the transmission system. The conventional solution includes building a new transmission line or adding on-site generation, as it can be seen in the first graph on the table. To comply with N-1 criteria, most-run generation is required, and sometimes it has to operate more time than needed, given the characteristics of the plant. The timing of the upgrades depend on the estimated demand growth, load shape, and the generation costs. Alternatively, the battery energy storage solution is shown in the second graph on the table. Storage can support the N-1 contingencies either by shaving the peak every day or being on standby. for charging automatically and discharging at the contingency time. It charges with cheap energy from the grid during off-peak hours. Storage behaves as an ideal electrical security resource, as a remedial action scheme delivering energy instead of sharing load. It can be modularly upgraded until a new line is required. This slide shows a potential battery energy storage project for Colombia for renewable integration. Colombia has plans to integrate 3 gigawatts of wind into its electric power system, which is about 12 gigawatts in capacity. A system reduction of inertia due to the addition of wind turbines would drive the frequency below the tripping point. We estimated that a 65 megawatt battery energy system restores system frequency response above the critical value of 59.5 Hz. The plots show the system response without and with battery energy storage system. A battery was found that can be 6 times more effective than a combustion turbine. UPME, the planning authority for the Colombian system, has been studying a battery energy storage system solution for the Atlantic region of Colombia for more than 5 years. The conceptual design developed by UPME was further refined during a project done by Quanta Technology and ESA, the transmission owner, during 2017. We found out that multiple coordinated storage systems can be effective for this 110 kV transmission congestion area. We found optimal siting and sizing of this battery energy storage system. Today, in 2020, UPME has launched the terms of reference to what it can become the first large energy storage application in Colombia to resolve subtransmission congestion. The solution is in the order of 80 megawatts for 1 or 2 hours. Regulations were also elaborated under a novel investment return scheme. In retrospective, the story around the Atlantic battery energy storage for Colombia can be extrapolated to other systems that are facing similar challenges. The items to review while evaluating battery energy storage for subtransmission applications include regional congestion, as this costs the markets hundreds of millions of dollars a year. Permitting and building new transmission line is time consuming and it is expensive. The line capacity is not modular, and relieving only moderate congestion may not be economical. Battery costs are dropping while transmission costs are rising, to the point where building new facilities may be impossible. The analytical consideration for battery energy storage includes congestion, which usually occurs under N-1 or N-1-1, a complete and thorough methodology that identifies the mechanics to determine the right size and location for energy storage is very important. Partial versus complete mitigation economics and multiple congestion facilities. Part G, valuation, business models, and the economic of energy storage. We will present an analysis of the value of energy storage from a utility practical perspective, and a study of the value of service, a variation by utility and the market, and a sample of the competitive landscape for batteries, power conversion equipment, and integrators. This slide presents an illustrative example of a utility that is a pioneer in energy storage projects. The breakdown of battery energy storage costs can be roughly divided by 55% the battery cost, 20% power electronics, and 25% the balance of plant, as it can be seen in the first chart in the bar. In the chart to the right, we can see that most of the benefits can be attributed to T&D upgrade deferral, which is rate-based, and the wholesale energy market, ancillary services, and energy market. Customer-side applications is the last application that produces significant benefits, which include demand charge and management arbitrage. These are very much tariff design related. The rest of the benefits are not significant or only significant on a project by project basis. As indicated before, a battery energy storage value location is key. This slide shows how the value that a battery energy storage system brings to the power system is different as adopted by the wholesale market, mainly the ISOs, or by the transmission and distribution utility. For the chart on the left, for ISO markets, frequency regulation in markets like PJM is by far the most dominant. Today, in 2020, growth on this market is quite limited due to market saturation. In second order, battery energy storage brings value in the energy capacity applications, with large presence in New York market in the US. Other values are spinning reserves and arbitrage, as you can see in the plot. For transmission and distribution utility applications, most of the value is on battery energy storage applications for islanding, as it can be seen in the first and second items on the chart on the right. In second order, battery energy storage brings value for applications in substations for 5 years of rate deferral. It must be noted, though, that distribution CapEx deferral for peak shaving is only viable in less than 10% of the cases. Stacked or shared applications that capture multiple value streams are much better and are the key to energy storage economic feasibility. This slide shows the competitive landscape for batteries, power conversion, and integrators. As it can be in the slide, the supply chain is deep, with many US and international suppliers in these three components of battery energy storage systems. Part H, Conclusions and Vision of the Future. We will present a summary of the benefit of battery energy storage projects and applications. Concluding on the state of the technology, technically everything looks good, but who's going to pay? Cost allocation methods for battery energy storage, grid technologies, how battery energy storage can be added to the list of non-wires alternatives. Utility scale battery energy storage is all about the business case. And at the end, a study process and project development approach for battery energy storage projects. A summary of the benefit of battery energy storage applications. Battery energy storage applications in the power system cover a lot of services in the transmission, distribution, or generation aspects. The main benefits of battery energy storage system applications to the power system are related to its bidirectional real and reactive power and energy capabilities. The main benefits are where the plus and minus real and reactor power interchanges are needed and in an intermittent and relatively small time intervals, which can range from 20 minutes to 4 to 6 hours. If and only if those conditions are met, are where the economics really play in our favor. To apply battery energy storage to provide capacity firming for renewables, to do time shift for electric energy and renewables, to provide fast frequency response, to provide inertial response, and to resolve sub-transmission congestions. Slide number 2 on summary of benefit of battery energy storage applications. Battery energy storage applications can be seen as a transformative technology, and it has several advantages that may influence the investment decision, including enables higher renewable penetration, is a incremental investment and a lower risk because it's modular and transportable. It can have the value of stacking different applications and therefore stacking different values, which can provide local capacity, grid reliability, and ancillary services, and can be competitive, particularly in urban areas. Also important, the battery cost roadmap is going down. Urban areas is where the Colombia case really made the economics play in our favor. Concluding on the state of the technology. In the US, the regulatory requirement in California to request 1.3 gigawatts of energy storage has had intense impact. Frequency regulation in the PJM footprint is a mature market with diminishing returns. We started with a movement in the West Coast and now it's moving towards the East Coast with a lot of activity in the utilities in the East Coast of the US. And started a distribution and now is fully engaged with transmission companies. What is the big thing on the storage? Battery prices are going down. Technology, the batteries and the BMS will continue to evolve. And now we are seeing applications in the order of 100 megawatts in the 4 to 5 hours energy duration. A few utilities are leading the space, as you can see in these slides. And control centers are also leading the efforts of battery energy storage with respect to the technology, particularly PJM, with frequency regulation, a mature market, and now starting to do more renewable integration. In California ISO, the Allison Canyon project that we share with you guys, that is part of the CAISO rules. Also some activities in another market like ISO New England and ISO in New York ISO. The technology has been proven. The question is, who is going to pay? New cost allocation models will have to be made for energy storage. The simple and more fair approach is to develop cost allocation models for each of the applications. The US has advanced in these matters, paying for capacity and paying for performance. There is still fertile ground for Latin American countries, as in the case of Mexico, Brazil, and Colombia. It will take serious work with the regulatory bodies to make sure the costs are allocated in proportional ratio of the direct beneficiaries. Colombia has started a good efforts on CREG Regulation 098 of 2019 and is worthwhile to look at. This table presents very high-level indications regarding cost allocation for energy storage services. We have the 5 categories for battery energy storage, and we present the different beneficiaries and the cost recovery methods. For energy supply, in which the beneficiary is the system, we can think about long-term contract with a capacity and performance metric as the cost recovery methods. Similarly, for ancillary services, we can develop an auction for service based on performance and also on the spot market. For system of the grid or grid system category, where the beneficiary is the local demand, we should develop a long-term contract based on capacity. For renewables integration, in which the system gets the benefit, a service auction based on performance would be the cost allocation method. Finally, for the end user applications where the beneficiary is the same end user, we can think about capacity charges, savings, and energy savings. This, of course, is at a very high level and has to be developed for the next level of details. Grid technologies, wires versus non-wires. Wire technologies are high voltage AC transmission lines and high voltage DC transmission lines. Non-wire technologies include static bar compensators, transistor control series capacitors, and battery energy storage systems. Battery energy storage systems can increase the utilization of the existing wire infrastructures, are quicker to permit, and they can be invested incrementally, and they are ideal for low growth scenarios. Utility scale storage applications. On the generation side, we can think about energy storage as a replacement for a peaker plant, solar plus wind plus energy storage, gas turbine plus energy storage, ancillary services, and also interconnection upgrades. On the transmission side, at the regional level, we can see energy storage to resolve reliability problems, market efficiency problems due to N-1 congestion relief, and to address policy driver objectives. On the local basis, reliability at the sub-transmission level, capacity problems due to right-of-way into the urban areas and the inability to build new transmission lines, resiliency due to black start, renewable integration, and transient stability. Having a thorough methodology is of paramount importance for the proper siting and sizing of battery energy storage systems. This is a methodology for the product development approach, which ends up in a project portfolio. We start with the target application areas to select the strategic market scenarios and define the system models. Based on that, we define the target constraints in a list to define optimal storage sites and sizes, and then define interconnection studies. We then start in item 7 with economic benefit analysis, and really item 8 is where we finish with the revenue stacking potential. The end results, we arrive into a portfolio of projects and solutions that are mutually dependent. To continue on the previous slide, having a thorough methodology is of paramount importance for the proper siting and sizing of battery energy storage systems. We start with the transmission network. Then we use the static model to study the reliability analysis using power transfer distribution factors and outage transfer distribution factors. A custom software is used to site the storage system, to define the right size of the identified storage location, and to evaluate the best fit solutions which are cost-based. We then start economic analysis and then perform to evaluate congestion relief, production cost, and the long-term economic relief. Finally, project economics include NPV analysis to evaluate the net present value and the benefit cost ratio calculations. Concluding remarks on battery energy storage systems. If a power system has aggressive goals for the penetration of renewable energy, such as solar and wind, and there is no roadmap for the integration of batteries as part of the solution, probably the chip is gone. The wide use of batteries for the integration of renewable energy for solar and wind is very important and has been accommodated. Battery energy storage systems, concluding remarks. If a power system has aggressive goals for the penetration of renewable energy such as solar and wind energy, and there is no roadmap for the integration of batteries as part of the solution, probably the chip is gone. The wide use of batteries for the integration of renewable energies such as solar and wind as a current theme has been seen in modern power systems. Thank you. These are part A, part B, part C, part D, part E, F, G, and H. I appreciate the time that we have taken on this tutorial, which has been virtual, and thank you for all your attention and support.